Hi everyone, Greg here. So I talked in a previous video about different levels of proficiency among programmers, the highest level being the Grandmaster of Code. And if we want to reach those higher levels, then I believe it is very useful to look at the layers below the ones we're actually using. And so today I want to explore those lower layers. Now, I do want to say I am not a chemist, I'm not a physicist. This is just my understanding of what computers do from the perspective of a computer programmer. What's the lowest layer you can get down to? Well, arguably, it's the periodic table. Now, when I was a kid, I think like most kids, I played with Legos, and in the box there would always be this leaflet showing a full list of all the pieces in the box and how many there were of each item. The periodic table is a bit like this leaflet for the whole universe. If you want to build anything, this is it. This is what you've got. Anything you're going to build, you're going to have to build it with this. Now, if we look at the first column here with hydrogen, the second column with helium. Now, hydrogen is very unhappy, very pissed off. Now, what hydrogen basically is, it's a single proton and then an electron spinning around it. Now, the reason why hydrogen is very pissed off is because he wants to have two electrons, but he's got only one. Now, helium, on the other hand, two protons and then two electrons spinning around it. He wanted to have two electrons. He has two electrons, so he's a happy guy. All the elements in this column, they're the happy guys. They've got what they wanted. And because they have what they want, they don't interact with anybody. They mind their own business and they're not interested in bonding with anybody. So those are they're called the noble gases because they don't want to mix with the other crowd, the ordinary guys. They're also known as the inert gases. Now, hydrogen is very pissed off because he wants to have two electrons. He's got only one. So in nature, you will never see H just by itself. You will typically see H2, which is where two of these say, look, we both want to have two electrons. We each have only one. What if we kind of stick together and pretend that we each have two? Okay, so the next one then is lithium. Lithium is also very pissed off because he's just one past being perfect. And so what lithium has three protons, then it has two electrons in one shell. They call it a shell. It's basically just like onions have those layers. Atoms have those shells. And then there's this extra electron in an outer shell. Now, because lithium is so unhappy, it doesn't take much to convince lithium to get rid of that extra electron. So this is how you could have a lithium-ion battery, where you basically have an anode which is coated in those lithium ions. You have a cathode, and an ion basically means when you have an atom and the number of protons is different from the number of electrons, that is an ion. So you have lithium coated here, and it's traveling from the anode to the cathode. Here there is an electrolyte. What the electrolyte does, it's preventing this extra electron to travel along with the lithium ion. And so the electron is forced to take the long way around, and it's going through the circuitry of your phone or your laptop or whatever the case may be, and this is how your device is being powered. The lithium ions is going from the anode to the cathode. The electrons are forced to take the long way around because the electrolyte won't let them through. So this is for lithium. Now carbon then. Carbon is the single most promiscuous element of the whole periodic table. Now carbon will have those 6 protons. It might have neutrons in there as well, but I'm just going to ignore that. It has those 2 electrons in the innermost shell, and then it has 4 electrons in the outer shell. Now the outer shell is known as the valence shell, and then the electrons are the valence electron in the outermost. So it has 4 electrons. So carbon is stuck in that halfway point. If you can't have 2 electrons, the next best thing is to have 10. 2 plus 8, right? 10 electron is the next best thing for the atoms. That's what they want to have. But carbon has 2. It's happy about that. But then it has 4. It's stuck halfway between 0 and 8. And so it has those 4 electrons desperate to hook up with just about anybody. And in fact, you have a separate branch of chemistry known as organic chemistry, which is dedicated to record and document the escapades of carbon. Then silicon. Silicon is like the shy big brother of carbon. Silicon also has those 4 electrons. So silicon here is 14. So it would have 2 and then 8 and then 4 electrons in the valence shell. Phosphorus would have 5 valence electrons, and then boron would have 3. So we have 3, 4 and 5 valence electrons. And so now you can do some magic with that. So now how do you do the magic? Well, you take quartz. Okay, now quartz is SiO2. What you do is you put it inside a furnace. You add coal. Coal is basically carbon. Then you heat it up. You're gonna need more carbon, more coal to do that. So you put it in the furnace. And then what will happen is the carbon will bond with the oxygen. So the oxygen is short 2 electrons to be happy, and carbon is short 4 to be happy. So you have 2 oxygen sharing the 4 electrons that carbon has. So you end up with CO2, which is carbon dioxide, and then you have the silicon metal. Next thing you do is you make the silicon into a crystal, and then you cut a slice of that crystal, which is known as a silicon wafer. So now here I have my silicon wafer. I designate various areas on the wafer, and then I use a technique called doping. What happens is in the crystal, all the silicon atoms are neatly arranged like a bunch of soldiers. With doping, here and there, you replace a silicon atom with an atom of phosphorus. And I do the same thing here. Now, phosphorus has this extra electron, and an electron is negatively charged. So this is known as N-type doping. Same thing here, N-type doping. What I do with the rest is another type of doping, replacing the atoms of silicon here and there with an atom of boron. So here and there will be an atom which is short an electron. So the lack of a negative electron, you could think of it as being positive. So this is positive p-type doping. So now what you do is you connect wires here and there. Now I call them wires. They're not really wires. You have to imagine grooves burned into the silicon with a laser, and then molten copper poured on top of it, and then the excess ground off so that it would be flush. I'm just going to call them wires because I'm used to it. But you have to imagine a closed circuit with a power source over there somewhere. So then you turn on the power, and what happens? Nothing happens. Now, the reason nothing happens is because silicon is a semiconductor. And in this present configuration, it's not conductive, and so nothing happens when you turn on the power. So what you do is then you have another wire. This is known as the gate. And you make the current flow with this gate has its own circuit. It's separate from this circuit. When you electrify the gate, it will produce this electromagnetic field. So when the gate is turned on, now the electrons are flowing through. So this is known as the source, and this is known as the drain. And so when you have, there's many different types of transistors, but in this type, the electrons flow from the source through the gate when the gate is electrified. So when the gate is turned on, we can represent this with a 1. When the gate is turned off, we can represent this with a 0. Now, transistors have their own symbol, and it looks something like this. Right, so this being the gate. Source and drain. And this would be an NPN type of transistor. A different terminology you might see is a base, the collector, and an emitter. Now, why the double terminology, I don't know, but that's what they use. Okay. So what happens is when the gate is turned off, this is not conducting, or in other words, it's resisting. By electrifying the gate, you can transform the resistance, or in other words, we're dealing with a transistor. Okay. Now, this is the symbol for transistors. I am just going to be lazy here, and I'm going to represent a transistor as a box with a T in it. I can have 2 transistors. Again, you imagine a closed circuit. Let's say I read the output here. and I can electrify the gates. I have them connected in series. So will the current be able to go through? Well, if I electrify this one and if I electrify this one, then the current will go through. If either one of those two is not electrified, or if they're both not electrified, then the current will fail to go through. And so the output I will read here will be 0. So if I call this A and B, I can create a truth table A and B. I can consider all the combinations. When both are electrified, my output will be electrified. In every other case, it will not be. So this is how you make logic gates. This specific one is an AND gate. And so I have A and B. In Boolean algebra, this would be written as a multiplication. Now, it might seem a little strange that we use a multiplication, because in common parlance, and plus are sometimes used interchangeably. But when you look at the truth table, you see that this operation behaves more like a multiplication. In electronics, the symbol, you would have, two inputs and then an output, so A and B here. And here have my output. This is an AND gate as it would be drawn in circuit diagrams. So here I have an AND gate. Rather than connecting them in series, I can connect them in parallel. I can read my output here. I have some way of electrifying the gate. I call this A and B. This is an OR gate, or in Boolean algebra, A plus B. So if I electrify this gate, the current will be able to get through this way. If I electrify this gate, the current will be able to get through this way. I can electrify them both. It's only if neither of them are turned on that the current won't be able to find a way through, and the output then will be 0. So again, considering all the possibilities, this is an OR gate. This is also known as the inclusive OR. And so that will tell you that if there is an inclusive OR, there must be an exclusive OR. When you don't specify which one you mean the inclusive OR. So the symbol here, same as the AND gate, except that instead of a straight line here, we have this curved line. So that's our OR gate. The last of the fundamental gates, the NOT gate. So I have a way of electrifying the gate here. I have a circuit. I will read my output here. Here I have a resistor. This resistor is weaker. It resists less than when this resistor is turned off. So if this gate is electrified, if it's turned on, the power will go this way, and nothing or almost nothing will go this way. If this is turned off, power will choose the path of least resistance, so it will go out this way. So I have only one transistor, or yeah. So A, not A, like this. In Boolean algebra, you might see this. You might see other symbols like this, or you might see this, different notations. And in electronics, it's represented like this. So that's my NOT gate. Then the last logic gate I will discuss is the exclusive OR. Also written like this, the exclusive OR. The exclusive OR equals A plus B and not A plus not B. So if I draw my truth table again, I have A exclusive OR B. This is true by definition. That is what I mean with the exclusive OR. So if I compare this, with the inclusive OR, if they were both turned on, then the output was 1. Here, if they're both turned on, the output is 0. Only if strictly one of the two is turned on, then my output is 1. So what if I have A plus B? A plus B is the OR. So OR is that would be the OR. Then not A, I will just inverse the things here. So this is not A, not B, is this. So if I do the OR operation with those, then I have like this. And then the AND, so I've this part here, and then this part here. So I need to AND those two columns. So the AND is the output is 1 if they're both 1. So there we are. This is indeed the same as the exclusive OR. So the AND, OR, and NOT gates are the fundamental gates. And with this, I can compute everything else, including the exclusive OR. And you see that this was true by definition, and this column and this column are indeed the same. So this is how you do the exclusive OR. The other ways of doing the exclusive OR right? You can, using the same technique I've used here, you can check for yourself that indeed this works. Those are different ways of doing the exclusive OR. Okay, so now NAND gates. NAND gates are basically an AND gate followed by a NOT gate. So the symbol would be like this. So just like an AND gate with the ball, a ball that follows. The truth table okay, so basically the inverse of what an AND would be. NAND gates are very interesting because with NAND gates alone, you can make a system Turing complete. Now, what does it mean for a system to be Turing complete? That is a whole deep subject in and of itself, but basically what it means is that the system allows you to compute anything which is computable. Okay, not everything is computable. Anything which is computable, you can do it. You can compute it with a Turing complete system. So, for example, you can create NAND gates in Minecraft. And so that means that Minecraft is Turing complete. The properties of Turing complete systems is that you can use any Turing complete system to simulate any other Turing complete system. So you can literally create an entire 8-bit computer within Minecraft. Okay, so this seems like a bold claim, a strange claim. So let's examine how this would work. Since with NAND gates you can compute anything, we should be able to simulate all the gates that we've seen so far. So what about the NOT gate, for example? And that one is very simple. What if I have a NAND gates here? I have the input A, and I use the input for both inputs, that one input A for both inputs of this gate, and I read the output here. What I have in that case A NAND A. So I have two possibilities. It's going to be 0 or 1. So if it both go 0 here, the AND will make it 0, the NOT will make it 1. If both are 1, the AND will make it 1, the NOT will make it 0. And that is indeed the same as the NOT. Okay, what is another thing that we could do? The OR gate. Let me see, where will I write this? I'm just going to write this underneath here. What you need to do for the OR gate is you have NOT A, which we already know how to do, and then you NAND with NOT B. So again, so I'm just going to compute those real quick. They're just the inverse of that. So I'm going to form 1, 0, 1, 0, 0. And then I need to NAND those two. So, well, if they're both 1, I will have a 0. In every other case, I will have a 1. So that's not A, NAND, not B. And then A or B. What is A or B? It is when they're both 0, I will have a 0. In every other case, I will have a 1. And then sure enough, those two columns are the same. So shall we do the AND gate as well? I might be able to fit this here. So this is equivalent to the OR. For the AND gate, right, so let's try this out. Both are 1, that will be a 0, it will be a 1 in every other case. And then simply notch this. And that, sure enough, is the same as A and B. So that works as well. The exclusive OR with NAND gates, how would you do that? Well, I could, since I already have the OR and the AND and the NOT gates, then I can just use any of those formulas to make my exclusive OR with the NAND gates. There is a more efficient way though. I got a diagram from Wikipedia and it claims to be a more efficient way of doing the exclusive OR with NAND gates. Now, maybe we want to investigate the claim just to see if it works. So I've just reproduced the diagram that I found on Wikipedia. I want to investigate if this is accurate. So I'm just going to label those NAND gates. I'm going to draw the truth table. And now I'm going to do A1, B. So the thing with NAND gates, if they're both 1, I will get a 0. I get a 1 in every other case. Let me try 2. I'm just going to write 2. Now the input for 2 is the output here and A, so I have to look at those two columns. So if I have a 1 in both columns, I will have a 0. In every other case, I will have a 1. Same with 3. So 3, I need to take the output from this column, and I need to look at B. So a 1 means there will be a 0. I will have a 1 in every other case. And then I click 4. 4, I need to look at those two. So if I have a 1 in both columns, that will be a 0. In every other case, I will have a 1. And this is indeed, okay, if I look at what the exclusive OR is by definition, those columns are indeed the same. So that worked. So with the NAND gates, you can do anything. This is very handy for some applications where manufacturers can just mass produce the NAND gates. It makes it cheaper in some cases. Now, my favorite mathematician is Gottfried Leibniz, and he made the remark at one point that doing arithmetic with binary numbers is very easy. So let's look when we do arithmetic with binary numbers, how easy it really is. So let's consider all the possibilities with the addition. We're just going to deal with single digits. So 0 and 1, 1 and 0, and then 1 and 1. And of course we're working in binary here, so this will be 0. There will be a carry. This is 1. 1, 0. In the other situation, there is an implied 0 here, so I could put another 0 here. What I'm noticing is that this position is 1 when strictly one of the two is 1, and in the other cases it is 0. Well, that's basically how the exclusive OR works. And then when both those are 1, then the carry is 1. Otherwise, the carry is 0. Well, this is basically how the AND works. So, oh, by the way, one thing I forgot to mention here is that the electronics symbol for the exclusive OR is like this. So, similar to the OR, but with this extra line here. So imagine I have those different digits, I call them A and B. I'm going to have my exclusive OR gate, and then I'm going to have an AND gate, and then here I'm going to read the result, and then here I'm going to read whether or not there's a carry. So if I build a box like this, I've basically designed a device which is capable of adding single binary digits. So this is known as a half adder. Right. So if there's a half adder, you will have guessed that there's going to be a full adder. Alright, so we have seen what a half adder is like. Now what does a full adder look like? Well, with a full adder, we are going to be able to add up not just numbers of single digits, but numbers of multiple digits. Now, you may have heard about 32-bit computers, 64-bit computers. Back in the 90s, you have 16-bit computers. In the 80s, 8-bit computers. So exactly what is 32 bits? 32-bit is really the size of a word. Now, what we mean with a word in the context of a CPU is it's basically the size of memory that is the most natural and the most efficient to be used by that particular CPU. So what we mean with a word is the size of memory which is the most natural and the most efficient to be used by that particular CPU. So now for the purpose of making it easier on myself, for the purpose of practicality, I am going to assume a 4-bit computer and look at how a 4-bit full adder would work. So I am going to add numbers A and B, but because they're now 4 digits, I'm going to call this the first digit, A0 and B0, and then the result, this will be the first digit of the result, R0. And the way that this works here will be a half adder, which we've already discussed. That's just the same thing, except that the carry, instead of coming out this way, now will go into the next component. So here we would have A1 and B1 being the next digit, the next 2 digits of our numbers. It begins the same. I need an exclusive OR, and I need an AND to figure out the sum and the carry. But now the result here has to be added with this carry. So here. And there will have to be a carry here. But when will this be a 1? Well, either those two are 1, in which case the AND will produce a 1, and there will have to be a carry, so that's a first possibility. So I will need an OR gate here. In this case, I get a carry, but there is another possibility. What if the result here is 1, and what if the carry is 1? In this case, this will produce a 0, but a 1 and 1 should produce a carry. So what I need to do here, I have a different AND gate. Like this. So the rest is just rinse and repeat. I'm going to have R2 here. I'm going to have R3. And now the only difference is that the carry, I also need to get the carry coming out here. What if I do have a carry here? If I have a carry in this case, that means that the numbers here were so big that the sum could not be contained in the 4 digits of my result. When that happens, we have something called overflow. Okay, so this entire construction here now is a full adder. So we've done the addition. Now, what about subtraction? It would be nice if I could do that next. So let's say I want to do 3 minus 1. Now, this is really the same thing as 3 plus negative 1. Now, I already have something that allows me to add. What if I could reuse that to subtract? What if I had a clever way of representing the negative numbers so that then instead of subtracting, all I need to do is adding. And this is exactly what computers do. Computers really only add, right? So how am I going to do this? Well, I'm going to use the 2's complement method. I'm going to take the 2's complement of 1, just 1, the 2's complement of 1 in order to represent negative 1. To find the 2's complement method, there are 2 steps. So I have my 4-digit number. The first step is I take the 1's complement. To find the 1's complement, what I do is I flip the bits. Now, that doesn't mean anything dirty. Flipping the bits simply means that I turn the 0s into 1s and the 1s into 0s. Like this. Then the second step is I take the 1's complement and I add 1. So this result here, this is the 2's complement of 1, and I use this to represent negative 1. So what if I try this now? I have 3. So what is 3 in binary? I have this. I add negative 1. So what's my result here? I have 1 and 1, 0. Carry 0 and the 1 be a 1. The carry 1 and 1, 0. I have a carry. 1 and 1 is 0. I have a carry. What do I do with the last carry? I ignore it. Just pretend it doesn't exist. That's my result. Now this is 2 in binary. 2 and 3 minus 1 is indeed 2. So this works. Now, this might look a little strange. It's like, what's going on here? Why does this work? Why does that series of steps lead me to be able to subtract by adding? Well, what I'm going to do next is I'm going to do those same steps, but I'm going to do them in base 10. And that hopefully will give us some insight as to what is really going on here. So now in base 10, I am going to do the same thing. So 3 minus 1. I'm still going to take 4 digits, but this time this is base 10. This is my first step. I'm going to do the equivalent of the 1's complement. How do I do the equivalent in base 10? What I will do is I will take the largest numeral in base 10, which is 9, and I'm going to subtract that first digit, and I get 9. And I will do that for every digit, so they'll all be the same. And then I have 1. Well, the first 3 will be the same. Then I have 1. So 9 minus 1 is 8. So I will get 9, 9, 9, 8. And then the second step is I add 1. So that will give me 9, 9, 9, 9. Maybe you're thinking, okay, is this really equivalent to what we did in base 2? Well, yes it is. We were flipping the bits. Now, what does that mean? I take the largest numeral in base 2, which is 1, and I subtract the digit. 1 minus 0 is 1. And then those first 3 will be the same. Then 1 minus 1 here is 0. So this is really the same operation. It's just that because we're working in base 2, it's the equivalent of just flipping the bits. Okay, so I'm going to take 3 and I'm going to add the 2's complement of -1, what am I going to get? I'm going to get 2 carry 0 carry 0 carry 0. A carry, what do I do with the carry? I ignore it, pretend it doesn't exist, and I have 2. Now what really happened here? 9,999, that's really the same thing as 10,000 minus 1. So to 3, I add 10,000 minus 1, and then I get rid of the carry, but the carry in that position is really the same thing as 10,000. So I do 10,000 minus 1, and then I take off 10,000, and then indeed that's the equivalent of just adding -1. Okay, so hopefully that gives you a better idea of why this 2's complement method really works, and it always works. Another interesting thing to note is that if I do this with 0, I take the 1's complement, and then I add 1 to the 1's complement. Well, all of those 1's are going to roll over into 0's. So the 2's complement of 0 is 0 again, which is a desirable property. Okay, so we've discussed the periodic table, transistors, logic gates, half adders, adders. What's the next level up? It is the ALU. Okay, the arithmetic and logic unit. The ALU is able to do basically all the arithmetic operations, so that is add, subtract. It can multiply, it can divide, and it can do a couple of logical operations. So that's the AND, the OR, the NOT, and then it will be able to do a couple of other operations beside that, like the shift. Now what the shift is, let's say I have a binary number, something like this. A shift is basically when I add a 0 at the end and all of those get shifted one position. So I would have something like this. That is a shift. And then there might be a couple of other things it can do, or there would be the modulo. The modulo is basically calculating the remainder after a division. The way that the ALU is typically represented is something like this. I would have my 2 operands, so the numbers A and B, and of course there isn't a single digit here, so you have to imagine lots of copper lanes representing all the separate binary digits. The same here. I'm not going to draw all that. And it can do many different operations. Since it can do all the different operations, I need to tell it which operation to perform. So each operation will have an operation code, or for short an opcode. So there'll be a separate number here I have to input to tell it which operation to perform. It will produce a result, and then it will give me a status. Now the status is a number which gives me extra information about what happened. So the status could indicate overflow. So the status could indicate overflow. We talked about overflow earlier, is basically when the result is too large to be contained within the number of digits provided. since we can subtract now, there could be underflow. There could be an error if you try to divide by 0, various things like that. And then I can give it extra information here as well, so there'll be another status here. This is an ALU, and obviously the circuitry here would be a lot more complicated, and all of the basic arithmetic operations are performed by adding. Okay, the multiply you can easily imagine. If I have 3 times 2, that would be 2 plus 2 plus 2. And then the division is achieved by successively subtracting a number, right? And keeping track of how many times you were able to subtract the number. What is the next level up? The next level up is an FPU. Floating point processing unit. So far everything we have done allowed us to only compute with whole numbers. How do we deal with fractional numbers? Well, if we have a number like 7, 7 is equal to 3.5 times 2, and that's really the same thing as 1.7 times 2 to the power of 2. And the idea behind floating point numbers is that everything can be written as 1 point something times 2 to the power of something. That's not 100% true, because you cannot write 0 this way, but almost all numbers can be written in this way. So this thing is known as the mantissa. This would be the base, and that is the exponent. If you have a 32-bit piece of memory, we use 1 bit for the sign. So this will be a 0 if it's positive. This will be a 1 if it's negative. We use 8 bits for the exponents. 8 bit for the exponent and 23 bits for the mantissa. Now imagine that I have everything set to 0 here. So it would be positive, the exponent would be 0, 2 to the power of 0 is 1, and I would have 1.0. Oh yeah, the 1 is implied, so the 1 is not actually stored, only this bit is stored and goes in here. So if everything is 0, we have 1.0 multiplied with 2 to the power of 0. This is basically 1. So programmers don't like it when you have just zeros which represents something other than 0. So for this reason, there is a bias introduced here. 127 is added to the exponent. With this system, you can only trust about 7-ish significant figures once you convert to base 10, right? I'm going to quickly draw the one for the 64-bit. So you have 11 and 52. So again, this will be the exponent, the mantissa, and this will be the sign. And with 64 bits, you can trust about 15 to 17 significant figures once you convert it to base 10. Alright, so what exactly do we mean with that? Let's say I have a number 123,456,789. If I store this in a 32-bit floating point, then I have about 7 significant digits which I can trust, and then the other 2 will only be stored approximately. So the actual value stored might be closer to 790 or 788 or something like that. So that's something to bear in mind, that with floating point you only deal with approximate numbers, and I'm going to demonstrate that later on with a little bit of code where you'll see that those numbers indeed are not exact when they're stored in floating point notation. So now how would addition work with floating point numbers? So let's take an example here. If I want to add this number, 1.5 times 4, which is basically 6, and I add another floating point number, this is 3.4. The first thing I notice here is that the exponents are different. This is basically 1. So that's the first thing I will need to fix. So this will be 3 by 2. And now I can just add up this. But now this is no longer in the form I wanted to. I want it as 1 point something multiplied with 2 to the power of something. So I have to do a couple of extra steps here. And that's still not good enough. So now this step here is known as normalization. All right, you put it back into the proper form. And you can clearly see this addition really does work. So this is basically 6. Here I have 3.4. This is going to be 8. And the entire thing will be 9.4. And you can easily check with a calculator if you don't believe me. But here we see that floating point numbers, for the addition at least, they will be less efficient because there's more going on. There's more work that needs to be done. When we look at how we were doing additions with our integers, with our whole numbers, this addition can happen in one CPU cycle. If you have one pulse of the electrons, once that the numbers are set up, one pulse going through the logic gates will produce a result. And how fast this happens will depend entirely on the clock speed of your CPU. Right? Here, this is a more involved process. It still depends on the clock speed of your CPU, but there's more things. There are more CPU cycles that will be used in order to perform this addition. Right? You have this extra step of normalization. You have to check the exponents. You have to add the mantices. There is more going on. I suppose we can quickly check the multiplication. I'll just do a quick example. The approach I will take here is that this time I will add the exponents, right? I no longer have to make sure that they're the same. And I will just multiply the mantices. And then again, I need to normalize. And again, we see that this works in terms of the result that we're getting. This is again 6. This is 6.8. and this will be equal to 40.8. You have again here a step, which is the normalization. So with the multiplication, you do have the convenience that you can just add the exponents, and adding is a much faster operation than a multiplication, even though you do still have more steps overall. Okay, so one of the very last things I want to show you is this little file here, floatingpoint.html. I will show you the code. It is a very, very simple page. You have the body of the web page. There's basically nothing in there, but when it loads, it will call this function. What happens inside this function? It will check whether 0.2 plus 0.1 equals 0.3. And if they are the same, as far as the computer is concerned, it will show up a little message box and it will say they are the same. If they're not the same, the message box will say they're different. Then the actual value will be computed and it will be written to the HTML page so that we can see what the computer thinks that sum actually is equal to. So what do you think is going to happen? I will double click on that, make your guess. What do you think will happen next? And it tells us that they're different. And you see it's really close to 0.3, but it's not quite the same. So, like I said, we're talking about approximate numbers when we're dealing with floating point. So this here would be the first significant figure, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So like I said earlier, you can trust somewhere between 15 and 17 significant figures when you're dealing with 64-bit floating point. And you see this demonstrated here. 16 significant digits are accurate, which of course is a lot of precision, but then after that it just falls apart. And this code therefore is not behaving in the way that you might expect. So this is of course an example I've chosen, especially usually floating point numbers are not a problem. They are accurate enough in most cases. You just need to be aware that you can have things like that that can trip you up. And this is written in JavaScript. JavaScript is a really bad language. I might make a video in the future as to why exactly I think it is a really horrible language. But in this specific instance, we're not talking about anything which is the fault of JavaScript. This is something intrinsic to how your CPU is actually dealing with numbers. So just something to be aware of. Okay, so for the last thing I want to discuss, this is a website. I'll have the link in the description. It does give me a list of various CPU operations and how expensive they are, how many CPU cycles are being spent in performing those operations. So you see simple register to register operation, add, the add, and we're talking about an integer add here, the OR, etc. And it tells me it takes less than one CPU cycle. Now, nothing can actually take less than one CPU cycle. It's just that sometimes the CPU can do several things at the same time, and so therefore it is averaged out to less than one CPU cycle. And then down here we have floating point addition, 1 to 3 CPU cycles. So this one, as you can see, and for reasons that should now be very clear, this is clearly slower than an integer add. Then we have a multiplication of integers and floats. So there's not a lot of difference between the two here. Then if we come down, we have floating point division down here. So we're talking about between 10 and 40 CPU cycles. And then integer division between 15 and 40. So you see they are in the same ballpark, but integer division can in some cases be actually slower than floating point. So if you scroll down on this website, you will get more details. Here you see the ALU, FPU operations. This is what we just discussed and it will give you more details. So to conclude, if you take away just one thing from this video, it would be the following. Whenever you use numbers in your code, whether you're coding in C or some other strongly typed language, I would suggest you always use integers whenever it makes sense to use them. The advantages you get is that you're dealing with exact numbers, and you get something that the computer can do very, very quickly. With floating point, you're only dealing with approximate numbers, and they're still very fast, but they're slightly less efficient for your CPU to perform. So this was it. I hope you enjoyed the video. I hope you learned quite a few things. Don't forget to like and subscribe if you enjoyed it. Thank you very much. Thank you for watching.